And the question is, we want to represent them at a mean field level. So that's what we did yesterday. And again, we always just write down our conservation equations. And here, the new thing here is we want to look at, for a swimmer located at position x0, what is the fluid velocity that we're getting at the field point x, okay? Because we have a distribution of bacteria or particles, we would want to add them up by weighting them with the probability density distribution function in space. So that's intuitive. And then the next ingredient in this calculation is, then the question is, what is this disturbance flow due to a single swimmer? And we'll talk about that because of Stokes flow. We can easily get that using our fundamental solutions to these equations. And then if you put that into this integral, you can carry that out analytically. And what you're left with is just, so on the left-hand side, if you look at the left-hand side, that's just the Stokes equations, okay? But now you have a forcing term, which you can treat that as an active stress due to the fact that there are swimmers in a fluid. There's an additional stress contribution to now the mean field, which includes both the fluid and the particles or the bacteria. So we looked at the stability yesterday, and these equations have a stationary fixed point, which is spatially homogeneous. So not a function of space, and also their rotational distribution is randomly uniform, okay? No bias at all. And it turns out that's a linearly unstable solution because the eigenvalue is positive. And if you do a full nonlinear simulation of these equations, you're going to see that as time goes on, you develop these patterns and bands of higher concentration and low concentration, as one would imagine that would happen. So the question is, so those are in free space, okay, without physical boundaries. And then the question is, what happens if we have a physical boundary? So here's an example where you have a circular container. And what we've discovered here is as you increase the activity, so there are two parameters that are of interest. One is the activity, that's just how fast these guys are swimming. If they're swimming faster, they're also generating more active stress in the medium. The second parameter of interest is confinement. And overall, we see in this case, one can identify. So to identify these states, you have to do nonlinear simulations of the equations, okay, in space. And then just look at what happens visually in the flow field. And in this case, you have three states, and we've talked about this already yesterday. And one thing I want to note here today is that if you look at a particular level of activity, say quite high activity, okay, as one might expect, if these guys are very active, so they're going to create a very chaotic flow pattern in the suspension. So that's what you see here in the red region. However, because we're on the confinement, so what you can do is you can shrink the container. So you can increase the level of confinement, and what you see is you're going to suppress this more chaotic flow due to the fact that you don't have enough space for that. And then eventually you're going to transition into a more steady vertical flow. And if you further confine them in the sense that your geometry, the shape of your container, the size of it, say is even smaller than your run length. So you cannot even fully achieve your step length. And in that case, effectively, your activity is lowered because of the confinement. So in that case, you reach a stationary state where there's no flow. And then in the circular case, you have a spherically symmetric density distribution. So we looked at that yesterday, and then here's a different geometry. So this is a concentric disks. And what you see here again for specific parameters, you see in this case a spherically symmetric distribution is developed. And let's watch this for a bit. It's just going to take some time. So this is now we've increased the activity and further increasing activity. Say a rotating flow that's developed here as it becomes more active. And if you're even more active, you're going to develop this chaotic flow once again. Okay, so that's sort of at least visually similar to the case of the disk. And Here's another interesting question.
Check the center, there are no particles.
So that's a wall, so it's a concentric geometry. Particles are only allowed between these two circles. This is a physical boundary, the white circle.
Check the boundary created or what's a create.
So it's a physical wall. Particles cannot get there.
It's starting there.
No, they can't be in this. This is a physical boundary. So the fluid boundary is the concentric annular region, right? You have two circles, and they're confined between these two circles in the annular region.
Is the fluid is in the this ring?
Yeah.
Which is there?
Yeah.
So there's actual wall which is
Yeah, that's right.
which is confining the fluid.
That's right. So there's an outer wall and the inner wall. So the fluid is in between these two walls. Yeah. Other comments? Yeah.
Where it is flowing the fluid.
The flow is generated by the swimmers. There's no
The fluid is
so it's a spontaneous flow. So there's no applied flow in the system. That's the whole point of the this problem we're looking at. So because these guys are swimming, right? They will generate their own flow, and in this case, they generate different kind of flow in the fluid depending on the activity and different geometry. Yeah. Okay, so here's another geometry, which is a racetrack. And what's interesting here is essentially in the transverse direction, it's very confined, okay? And if you watch this video, what you see is, again, you have a state where nothing's happening, and as you change the parameter, so in this case, the height is shrinked, and you see you develop this systematic flow that's in a particular direction here. So essentially, you can use these geometries to control the flow, and you can generate a directed flow. So, for example, in this geometry.
so this is for a constant alpha at this.
Yeah.
Activity is very high.
In which case? This case? Sorry.
Yes, this is
Yeah. Now we're also changing activity. So if you look at this case where this pathway S is 1, okay? And in this video is 0.6. Yeah, so it's changing.
So this is basically projecting the hydrodynamics of fluid,
Yeah,
which is confined in this geometry,
that's right.
and it is embedded with active particles.
Yeah,
So is it the
Yeah.
case?
that's right.
So the movement is of the fluid or of the active particles, or the fluids are fluid is moving like that.
Yeah, this is a fluid that's moving.
So, but activity
Then-
is not related with the fluid.
It is. So that's what's driving
Activity
the
is
yeah,
related with the active particles which are dispersed in the fluid,
yeah, and they're driving the
and
flow.
the fluid is moving.
Yeah, but they're also moving with the flow.
The active particles are moving with the flow.
Yeah, but the flow is generated by themselves.
Flow is generated by themselves.
Yeah.
So flow already.
Yeah, so if you kill these bacteria, there won't be flow.
There
So
is
it's
no-
generated on their own.
No. So no. What I'm asking is that the fluid is there.
Yeah.
In this geometry, you can make it like this shape, or it's a channel.
Or you can make a flat channel. That's
It's a
fine.
channel.
Yeah.
Okay. So the fluid is already there in this channel.
Yeah.
And fluid is actually moving. Okay.
No, if you don't have bacteria, they're not.
So if bacteria are not there, then the fluid is not moving. So
No,
fluid
yeah.
movement is created because of the activity in the bacteria.
That's correct.
Okay.
Yeah. So that's
So,
correct.
so
Yeah.
depending upon the activity,
Yeah.
you are getting this flow from the water.
Yeah.
Okay.
Yeah.
Of the solvent.
That's right.
There.
That's right.
And that is making that pattern.
Yeah. Yeah.
So what we can infer from it actually? So how this is being created because of this?
So it's easy.
And
Yeah.
not only this, second
Yeah.
question is that in what kind of physical situations such results may be useful to visualize something which is happening now.
So this is useful. Is one example is for microscopic flow actuation, where you have these active guys in there, and then if you get to, for example, in a channel-like structure, as we've seen here, it's quite easy to achieve a directed flow. So that's one application that can be useful. In terms of how to infer which state the system's in, so that's very non-trivial because this is a fully nonlinear system. So the only tool we have at this level is the linear analysis, which is not going to predict this. Okay, so this is a fully nonlinear regime.
So one other question which I would like to continuation of this, that you said I understood that the fluid is there, it is still, it is still means not moving,
That's right.
and then you disperse bacteria with certain activities, and then because of the activity of the bacteria, this fluid is making these patterns and it will start moving. So is it the bacteria and the solvent interaction which is playing the role?
That's correct, because when bacteria move or any object moving
So
the
there
fluid,
will be two type of interactions. One is the bacteria interaction,
they're all included.
which okay.
Yeah.
But in models, whether we consider this bacteria and bacteria solvent interactions,
Yeah, they're all there.
they are
So the bacteria interaction is also mediated by the flow.
mediated by the
Yeah. So they're all included. That's correct.
So, but there may be two different contributions to the bacteria interaction. One, that if fluid is not present, okay, then even then the bacteria can interact with them. And there is another contribution, which is the indirect one, mediated by the fluid. Is it both of them are?
But actually, when we think about this, you can't have the first case because they're always in a solvent. So in the previous models we looked at, we neglected the fluid-mediated interactions entirely. So whether it's two bacteria swimming in water or more, so their interaction is only mediated by the flow. That's the only mechanism.
So the one interaction is there, which is mediated by
Yeah, because we're in a solvent. So
direct.
yeah, so it's not to sort of dry active matter systems like robots on a platform. In that case you have contact interaction. So here it's all mediated by the fluid.
To be clear, no direct packet.
No,
It's the interaction. It's the one interaction which is mediated through the fluid.
that's correct. Yeah,
The one
that's correct. Yeah.
so it's highly direct.
Yeah, exactly. Yeah.
This interaction will also depend upon the extreme with which the fluid is moved.
It depends on.
The movement of the fluid.
So the movement of fluid is driven by the bacteria. Yeah. So it's a two-way coupling. Okay. So you know bacteria moving around generates flow, but at the same time bacteria has to move with the flow that they generate. Yeah.
Suppose a single bacteria is there.
Yeah.
And if it moves,
A disturbance flow. Yeah.
it is a strain
Yeah.
which is transmitted to the.
That's correct. That's correct.
This is the cascade which happens.
Yeah.
That's why it's here.
That's right. So if you can, you can imagine if you have one bacteria in water, sure, it's moving around, it generates a flow, but then if you put another guy in there, it's going to feel the flow that's being generated. But at the same time, the second guy is not going to generate their own disturbance. So they're all included, but they're all mediated by the flow, the interactions. Yeah.
Sir, if I remember correctly, yesterday the disk figure.
The disk. Yeah.
We told that this is the probability density. The heat map is actually of the density function.
You mean this one here?
Yes. No. In all the simulations.
Okay. Yeah.
So the heat map is basically of the density of the particles.
Yeah.
Right. If I understood.
Yeah.
So that means whatever activity we are seeing is I mean to say is the flow of the particles, not the flow of the solvent. Right.
No. There are two things that's shown here. So you have the concentration of the bacteria. You also have the streamlines that are shown here. Those are the white lines here.
Oh, good.
So if you watch the one here, we see this not.
Sure.
Yes. Okay, see these lines? But nonetheless, this density is moving around, right? So that's all. You can also see that there's flow going on. Yeah.
So the red means that more bacteria is
Those are the higher density bacteria. They're moving around. They're being transported. So that's the flow. That also reflects the fluid velocity.
But that basically is established.
Sorry?
Yeah, almost periodic.
Yeah. In this case, you get a quite regular structure. Yeah.
So my confusion is the figure showing the probability density?
It's showing both on laid and overlaid on top of each other. But even just looking at the density, you can see it's moving around.
Yes.
So it's time dependent, which means it's being transported. Okay. But yeah, there are two things that's being shown. That's why you have the lines and the density. That's correct. Yeah.
Yes, sir. So sir, are the lines a result of, is it a consequence of the simulation?
Which lines?
The strain lines.
No. Those are so you do the simulation and then you solve everything. You have the flow field, right? And you have the particle distributions, and then you're just using the data to visualize what's happening.
So we are plotting the particle.
Yeah, we're plotting the density, and we're plotting the streamline of the field, flow field.
So it's an overlapping plot of.
Yeah, it's just plotting. It has nothing to do with physics. Yeah. You can also just look at the flow, and then plot it to see what's happening with the flow. Yeah, that's fine. Yeah. Question. Yeah.
Yesterday, obviously you have said for this year, so particularly you have said that bacteria will be the.
Yeah.
And yesterday you have told us for the vibrate structure, the bacteria was going against the flow.
That's a different. That's a different problem.
The different things.
In that case, the flow is applied externally, and we're looking at a single bacteria moving in that flow. Here we have many bacteria that are generating their own flow. There's no applied flow in the system. Okay.
So if we apply the external flow, let's say, so the movement of the bacteria will be reversed, or it will be in the same direction with the flow.
It depends on context. Then, if you apply external flow, then you have to have like that piece, right? Then bacteria will move with the against the flow, but also they're generating their own flow. And the question is again, as we see in the previous problem that you talked about, it depends on the speed ratio of the applied external flow and their own swim speed. You can imagine if the external fluid velocity of applied is much higher, then they're not going to go against the flow. If they're comparable, then they will. Yeah. Other comments? Okay, so you can do all kinds of simulations with this system. So here's another example that we're going to show. So what happened here is you have a thin band of active fluid. That's the water with bacteria. But the other regions are just pure solvent, okay, just pure water. So we're looking at active matter invasion of a viscous fluid. So this is a sequence of simulation images. Essentially what you see here, if you have a flat band, that's unstable, we established that. And what you see is it develops this, again, in this case now we have removed the boundaries. So it's a periodic domain without boundaries. And as time goes on, you see again, we develop these chaotic structures. And depending on different parameters, the details of the transient dynamics are somewhat different. But the point is when you don't have boundary, if it's active enough, you always get a very chaotic flow pattern, okay, that emerges.
In the simulation, you use working boundary conditions.
In which case? In this case, there's no boundary. Are you talking about the previous case? So this is a periodic box. So it is simulating the box behavior. Yeah. So when you have an actual boundary, then you have a condition on the probability distribution saying that particles cannot escape into the wall. So you have a no flux condition for the probability. And for the flow field, you have a no slip condition saying that at the wall, the fluid velocity is 0. Right here, because we don't have boundaries, just periodic to mimic the bulk behavior. Yeah.
That here in numerous boards, and each board is a type of batteries in generator. So here.
Are you looking at the horizontally or?
It is
So this is over time.
over time.
Yeah.
That is the time evolution.
Yeah, so this is time evolution. So we start from this flat, nice structure, right? As a initial condition, that because simulations as a initial state, and then you just let the system evolve over time.
At the last one track,
Yeah.
and the after sustained long interval of time, it is almost uniform distribution.
In this case, it's more homogeneous, but this is only a time instant. The flow will never reach a steady state, because it's chaotic. Yeah.
So what is the difference going negative to alpha is lower here?
What's the difference? So in the top case, so in the bottom case, the activity is different from the one at the top. That's all. Other parameters are the same. Yeah. Other comments? Okay, so there's also a video associated with this simulation that we can look at. So in this case, again, we have a thin band of polars with a particular level of activity. And we're going to look at, in this case, these things are plotted separately. To your point about what's actually we're looking at. So in this case, we're going to first look at the concentration, I think. So then now it's just the concentration, okay, of bacteria. And then we're going to look at the polar order. And then the fluid velocity.
Well,
okay, so that's the one example at the top, the one in the image. So this one, let's see what's different about this one. Okay, good. So here we have to wait. Sorry, 1 sec. Yeah, this one. So here's a different parameter. So this is quite active. You see, quickly they establish these chaotic patterns. And again, this is the polar order over time. And lastly, the flow field.
these are the solutions here.
Yeah, these are simulations resolving the full equations that we talked about. Yeah. So, as you have seen up to this point, these kind of mean field theories are always, you get nonlinear systems of equations. So analyzing them in an analytical fashion is difficult. Often you only have nice results in the linear stability analysis. Even those equations actually, you can derive the equations, but the equations you get in terms of the eigenvalue problem often also have to be solved numerically because of the complexity of the equations. So things are not as nice as what we've seen before in the dilute cases. Other comments about these simulations?
This question would have moved by the microscopic order equations also, or?
Okay, good question. Let's go back to you could, but then you have to you still want to incorporate the aerodynamic interactions in there. Yeah, you can do that. That's fine.
I'm just saying that in the like n systems, you have to consider the hydrodynamic interactions.
Yeah, this is considered. This is not a very dense system, but we have aerodynamic interactions here.
But we can actually take it in systems and just take interactions and when we go up, integrate the hydrodynamics and we do that.
So you want to just have contact interaction
Yes.
among particles without the hydrodynamic interactions.
You're saying that interactions of the linear equation.
Yeah.
Using interaction in linear equation.
We talked about that already, right? But
Yeah.
we have found that already. But if you want, the point is we don't need to include hydrodynamic interactions. You can also do that in Einstein equation. It's just you include the forces you get from the other particle, right? So you go back to we got somewhere here. Here, right? So this is how you incorporate the hydrodynamic interaction forces with multiple particles. So I've written this equation for a single particle. You can imagine you can write this for n particles. So you just stack up. So this will be F1, L1, F2, L2, and then U1, omega1, U2, omega2 all the way. And then this matrix is, so you can imagine it's augmented, very large, right? Then you can incorporate those into your equations. So conceptually, it's not difficult. The only difficulty is in computation, is computing these matrices. Conceptually, it's the same way of doing what we've been doing before. Okay, does that make sense? Other comments? Okay, so we looked at sort of semi-dilute systems where particles don't get very close to each other. So we didn't, and that when you want to think about more concentrated suspensions, typically we want to also include some sort of alignment or contact interaction into these equations. So one way to do that is to introduce a phenomenological model for alignment. So this, for example, this is one way to do that. So let's try to think about what happens with this kind of interactions. So I'm going to switch to the tablet. Okay. So just to recap, we had the following equations that we were looking at. And we have a mean field flow generated by these guys. Okay, so the question is, can we generalize these equations to incorporate some sort of, say, nematic alignment interactions? Which will be useful when you want to think about even more concentrated systems. So when you increase the particle density further, so one way to do that is to introduce a phenomenological potential for that. For example, the one that one can do, this is essentially borrowed from classical liquid crystal theories, okay? I can introduce a Meyer-Soft potential. There are other types of potentials one can introduce, but this is one of the simplest. So for example, we would have so this depends on a pair of particles and their orientation, right? We want them to align with each other. So we can write it in this way. So this number here, this constant, that's essentially the strength of this interaction, U0. And then we want to incorporate this into our equations. So because again, as we did in the mean field of the velocity, we have a particle distribution function. So we just need to average over.
We want any constant.
A U0 is a constant.
Just to
You can tune the value.
Yeah, so you can increase or decrease if you want to think about trying to match it with.
Q prime is basically the angular parts
Yeah, so that's two. Yeah, right.
in the form of the square.
Yeah, so this is a Q, that's the first guy, okay? And the other guy is here, say, that would be Q prime. Other comments? So want them to try to align, and if you increase U0, then they're gonna be strongly aligned. So again, we can make use of the same mean field approach, just average over the distribution function to get my mean field potential that a particle here is gonna experience.
It's three dimensions.
Which one?
these particles are in three dimensions, not in
Yeah, these are general equations because we're yeah
3D.
yeah yeah. It can be 2D or 3D.
To be just a part.
Yeah, you 2D you can expand this out to a one angle. That's fine, but yeah,
A combination of side and full side.
that's right. Yeah, yeah,
Like we some past spine one right describe
yeah, yeah, yeah. Exactly.
field.
Right, the see.
You can you just write yeah. So this is general derivation. So you can just write Q as a you know in 2D. Let me just write this down instead of just saying it. So in 2D you would again you just write Q as an angle, right? And then you can write it down. That's fine.
Yeah.
Yeah. But in the way where yeah
Use side to side theta cos.
yeah in 3D yeah yeah
Theta should be.
that's right. But we want to do one
When
derivation.
you multiply,
Yeah.
you get the combination. Of
Yeah, yeah. So we want to do one derivation. So I'm not going to write that out in just 2D.
Yeah. Okay.
Yeah.
Yes, sir. So it's a good exercise to find out what is the Q dot Q prime in 3D.
Yeah, we'll do some of those algebra on Saturday
Yes.
as well. Okay, so
Yes, sir. Right.
let's do an mean field average of this potential to get what I'm fearing, what I'm getting on the mean in the mean phase sense at x and q. So I will be integrating the distribution function at x q prime t, then this k here, q prime, q prime. Okay, so this is in the same spirit as how we did the flow.
Then let's see what key doing.
Oh, k is this one. Yeah, so that's just two particle interaction.
Like
So this is two particle interaction potential, right? Essentially, and what we want is we want to have a mean field representation.
what is the sort with EY and so with that?
Yeah, yeah,
You know, the like makes me worry into that. Because the whole
the mean is here, but that's the k that at the top. Yeah, that's just two particle triangle line, right? And the bottom here is just making a mean field representation. Yeah.
contributes to that. All of it one inside the suspend are freely design out.
Yeah, so you can imagine,
It was this year.
right?
And that you know, I was tweaking.
Yep. So this is at position x and q, right? Position x and angle q, but there are other guys around me. So those are all q primes, but there can be multiple of them. Yeah. So you can visualize. That's why you have to integrate against q prime. So that's my neighboring particles.
The equations are actually not same, but they are all the particles feeling the potential which is
Yeah, the position is the same, so they're nearby. Otherwise, they wouldn't align with that. Yes,
because of that interaction they start aligning.
that's right.
So that by with the change of those
Yeah.
thermodynamic conditions.
Yeah, yeah, yeah.
Yeah.
Other comments? Okay, good. So turns out again, the reason we take this simple model that people like to use is you can carry out the integral exactly. Okay, so let's try that as an exercise. So we have this one, and what we want to do is
So,
question. Yes.
so as a mini being used X and U or for X, you know, the the less at the S and Q, then how when it is how when it is to when I the
So that would be the mean potential from my neighboring particle. So you can look if you look at this sketch here, right? I'm at this position.
this
The alignment interaction only works locally, right? I'm not going to align with someone further away. So I just take the all possible other particle orientations, right? So you fix a particular q prime, you get this k q prime, but there are other particles. Their distribution is described by this function. So I just average over that locally. Local means locally in x.
can still look
Yeah.
I don't understand what the ability to distribution
It tells me what is the orientational distribution, q prime, right?
because
The mean of,
it doesn't mean key.
yeah, it is. You add them up because it literally adds up. Yeah. Right. Because the swimmers' orientations are randomly oriented locally.
So people are going to send WhatsApp, but they can even view as still be like a familiar as if
Yeah.
the import doesn't mean and that's slower than the other.
Which deviates.
The mean view.
So that's just the net potential I'm getting from my neighbors. So I'm trying to align with multiple particles, right?
Then
So then what the result of that is I'm trying to align with the average
go to.
or the sum.
So you can have them
Yeah.
there the blood.
Yeah. 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 So yeah, exactly. It's just the average orientation. Yeah. Other comments? Okay, so let's try this. So we have this alignment potential in mean field, which means in our equations, so this one is still the same. And the only thing we need to modify is the rotational flux, because now I have an additional rotational component due to the alignment potential. And the way to calculate the angular velocity I'm getting is to take the gradient of the potential. Okay? So we take the gradient. And more specifically, taking the rotational gradient.
Still, we are treating particles as passive.
In which case?
In this way.
No, particles can still be active.
Active.
Yeah.
So what is the term which needs with the active? We give you particular.
Here, it's not in here. It's still in the original equation, right? So these are still the distribution of these active particles. So it's just on top of their being active. When they're dense, they also tend to align because of their.
They are trying to receive.
Yeah.
What is that? If we have this particles,
Yeah.
and you change the thermodynamic condition because of this interaction, they will align.
Yeah.
Okay, this is just because of the excluded volume.
That's correct. That's correct. Yeah.
Now the point is that, and this is going to happen if you change the either temperature, you change R, you change the.
But in this case, it's just the concentration. Yeah.
So both can play the role.
Yeah.
Of this increasing the strength of interaction,
Yeah.
which will lead to the alignment.
Yeah.
Now the point is that we are talking about these systems made up of several particles.
Yeah.
Okay. Anyhow, we can see the alignment. Now we are talking about the active ellipsoidal particles.
Yeah.
So, what are the extra terms or the extra contributions we are introducing into the model, which leads to the activity, so that we can say that these particles are now active.
You still just add the swim term here. That's not changed. So I'm not changing the active description. I'm just adding to the fact that in the previous model we're saying that the system is fairly dilute. Okay, so there wouldn't be alignment interactions because the probability of two guys get close to each other is very small. In this case, we're just increasing the density now. The active description is still the same. It's only now we want to incorporate an additional alignment because now they are much dense than before.
So do I tell it the activity is coming because of just the hydrodynamic interaction?
No, it's still they're self-propelled and they're still self-propelled.
Self-propelled.
Yeah.
That's what I'm asking. So
Yeah.
So we have a system where the several particles are there.
Yeah.
Now I'm saying, so we consider with the passive.
No, these ellipsoids are self-propelled. Yeah.
Yes.
Yeah.
So what I'm saying, whenever we are making models, okay, is there any specific terms in any way, okay, we are introducing and we are saying that these particles are self-propelled?
Yeah. I mean that's still the same as before, right? You have the wait. Sorry, what's happened here? You still have the swimming motion in the probability distribution.
So this term has been added from outside.
Which is being added back from outside.
Where's this?
I think, when it was passive, it was just the.
This term was zero.
Yeah.
When it was the particle is passive, this term is zero.
Yes, correct. Yeah.
And in this list, so this term is actually giving rise to the the activity.
That's correct.
It's making the particle active.
That's correct.
Because the swimming speed we are adding from outside.
Yeah, yeah,
And this swimming speed is constant. We can tune it.
yeah,
It doesn't depend on the position or time or something.
yeah, yeah, yeah. That's right. Yeah.
And this is still there.
Sorry. Yeah, that's still there.
It's
yeah.
still there.
Yeah, yeah,
So we are saying now that instead of spherical particle, we are having an absolute particle.
yeah, yeah.
Okay, but the interaction between them is now being modeled by the Mershoff model.
Yeah.
And then
But that's only for high density. Even if the ellipsoid particles are very dilute, we wouldn't have that because that effect is very small.
interaction will be very weak.
Yeah, yeah,
That's why.
yeah, exactly. Yeah,
So we are in the same situation.
That's
but
correct.
Now instead of having spherical particle, we are having
Yeah.
ellipsoidal particle.
yeah.
That's all.
Right.
And we have a form of the interaction.
That's right. That's all. Yeah. Good. Yeah, yeah.
I have a question.
Yeah.
Like, shape part is taken into consideration by the Marx square potential.
The alignment between
Yeah. So that just because like the shape has changed to the ellipsoid, they are aligned.
and only when they are dense. Yes, correct. Yeah.
For that, like we consider the shape part. We are
So there's another place that the shape enters in the equations, which is the angular velocity. So the angular velocity of a spherical particle and ellipsoid particle is different in the flow.
because like this should be zero. This potential should be zero. So spherical particle, right?
Yeah, even if they're dense, because they don't align, they decline, they're
Spherically symmetric.
Yeah, yeah, exactly. Yeah. Good. Other comments? Yeah.
Bear with me, I'm a bit confused.
No, that's fine.
So when we were doing particle interaction and we had written the WC potential, in that case, we were doing it for one particle.
Now that's a dry system where we do not consider the interaction needed by the fluid.
Yeah.
So we're literally thinking about balls colliding with each other. Okay. So that's modeled by the WCA potential. It doesn't have to be one. It's multiple particles. If you have one particle, then there's no interaction with other particles because you have only one.
Right.
Yeah.
The only difference is that there was no fluid. So
There we don't model the fluid motion.
Fluid model.
Yeah. So that's the simplest model, right? It's like in the first lecture talk about how to classify systems. That's a dry system, in the sense that we're not including the effective flow. So we're essentially making our models more and more realistic.
Yeah. So here, the difference is because of the interaction mediated by the fluid. The difference is manifesting in the potential.
No, the potential is still a alignment interaction. The fluid interactions we already represented in the previous talk, right? So now we're thinking about the fact that these are actively ellipsoid particles. When they are very dense, they tend to align. Whereas two spheres, they do not do that because their collision is spherically symmetric.
Mainly the fluid mainly is the U and omega, right?
Yeah, that's the one we did last time. Yeah, right.
And with that, we are saying that there is an alignment interaction. This is the
So on top of that, this is yeah.
Can we keep it if it
Because I think also along the same time as Professor was asking, this continuity equations that we had to begin with, this del P del T and this the gradient of flux times.
Yes.
This is same as for the triactive particle right now.
That is always the same.
That is always the same.
So if you don't look at the flux vectors,
Yeah.
that is always the same. That's governed by conservation. These are called constitutive relations.
Right.
The reason I call that is they depend on the specific case you're thinking about.
Right.
Yeah.
So what? So that JT, right? So
Yeah.
there is. Let's say when I have active dry particles, I still had the USQ beta.
You don't have this flow, you turn this off.
We don't have this. Okay.
Yeah.
Okay. Not
Right?
Okay.
So the terminology here is important.
Yeah.
When you call these constitutive relations, you mean that when you have a different situation, that will be different, right? But the conservation law at this stage is always the same. Yeah. Yeah.
I want the question is that can still understand the alignment to that when right?
Yeah, you could. Yeah, exactly. You just have particles. You're not considering fluid interactions. You have two hard ellipsoid particles. They will tend to align as well, right?
The identical interaction
That's-
is
yeah.
taken into account by U and omega.
Yeah. That's because we're in the fluid now. We're not looking
The
at.
activity is by US.
Yeah.
And then we are adding on the top of it an alignment.
Yeah.
Just if we cancel all of it, it will just be again down.
Yeah. So this is.
Alignment will always be there because see, in order to reduce the entropy, now because of the alignment, there is an option that to align it.
Yeah.
Because see, the particles are they can look at it. They can use entropy can be reduced by just by coming to there is an hardening which is forced to be there.
Yeah.
And this is just because of the exclusive volume.
That's right. That's right.
Yeah.
Yeah. It's volume
That
exclusion.
we are giving directly.
Yeah. You're modeling that. Yeah.
Makes sense.
Yeah. Other comments? Okay, so let's try to carry out the mean field calculation. So we want to take the gradient of the potential, the orientational gradient. So let's take this to that. So essentially we want to calculate this quantity, right? U of x q t. So that's what we want to do. So let's do this part first. So I'm going to take the derivative first and then take the cross product from the left later on. So then we're going to differentiate u with respect to q, which becomes, so if we go back here, well, that's fine. So I have an integral of p x q prime t, then the derivative of k with respect to q, right, dq prime. So we just need to differentiate k essentially, and k is given by minus u naught q dot q prime squared. Okay, so let's take the derivative. This one is easy to do, so you have minus 2 q dot q prime. Then you want to differentiate q dot q prime, right, with respect to q. Yeah, it's a quadratic function. But q prime has nothing to do with q, so what we want to do really is the following. The derivative of q with respect to itself. Question, yes.
It's the professor was saying that we need to align a vector with x to reduce.
Yeah,
And we're trying to model that in this way.
that's correct.
So I'm just saying that can it emerge? So like,
You do a particle simulation, you emerge, you do a Brownian dynamic simulation.
over there we don't keep this kind of interaction.
There are two ways to do it. One is when you do Brownian dynamic simulations of two ellipsoids, if you precisely resolve the contact forces and torques you're getting, you're going to emerge a alignment.
So I'm saying that this is a potential, we're trying to model it. Right?
Yeah, because
We are modeling it and we own that into that.
yeah. So if you want to build actually what you have to do always is you start from the micro mechanics or the Langevin equation, nonlinear dynamics. And in this case, you have, say, ellipsoid particles that are moving in a system. You have to actually resolve the contact forces when they come close, right?
Contact forces like when they come.
When they come close, there is a force of contact. So you have an ellipse like this. You have another guy coming in this direction. What happens?
This right.
No, you have a force at contact exerted by these guys, right? Same as if you push against the wall, what do you get? The wall pushes against you, so that's the same thing here. You have two forces that's coming. Okay, make sense? And furthermore, if you look at how the force will, what the force does is if you look at two particles that are coming together in this way, okay? So the force here, so say this is 1, this is 2. So what's the direction of the force that the particle 1 is going to get? In which direction would that be? This direction, correct? What about for particle 2? Sorry? Why not? They're contacting. It's Newton's third law. Has to be in the opposite direction. But if you look at the effect of this force on particle 1's angular motion, you get a torque, right? Because the force is off center. So you take the momentum arm here times this force, what do you get? Where do this guy rotate? This way? What about this one? The other way? What does that do? Align, right? You're aligning them.
So we can then compare both of them.
So what you have to do is you want to represent this accurately. You have to do the micromechanical modeling of how the force gives rise to alignment, but you can't do that here in the mean field sense. That's why we're taking a simple potential to represent that. Does that make sense? Yeah. So actually, you have to do a lot of work in this context, and we have done that. I don't have time to talk about this because this is very involved, but you can do it if you want, and then you don't have to do any modeling of it, because this will emerge. The alignment emerges from.
Then we can compare this with the link field.
You could, yes. If you've done all the simulations, you can compare. Yeah.
Let's see.
And the question is, as you might have guessed, this can only represent that, qualitatively. It won't be exactly the same.
Exactly.
Because clearly this is more complex than that. Okay? But anyway, you can do it if you want. Yeah.
But the other way of understanding the same thing is that you got to see the reverse against. Here in this model, we have introduced traction. And if you, with that interaction, if you do solution, you will get the right.
Yeah.
But in experiments, we know that the alignment is there.
Yeah.
Okay. Now the point is that alignment is there. So what we have to understand that some sort of interaction is playing some role in
Yeah.
whatever way it's coming into the picture.
Yeah.
And that is being modeled by the theoretician. That okay, if you introduce this kind of interaction, we can get alignment that we have seen in the simulation.
Yeah.
So this is the other way about it. This is just the exclusive to adjust more and more particles, and so they get alignment if you increase either the concentration or decrease the temperature at the same concentration.
Yeah. Yeah.
So so it both ways. If they are aligning, so we have to make a model to get the picture in the simulation.
Yeah.
So we have to do some kind of simplest kind of interaction which will give rise to this.
That's right.
So this happens naturally as you expect.
Yeah. Yeah.
Yes.
And to your point of so you can have other more complex.
Micromechanics is exactly, the experiment just told about it, right?
Yeah. So if you do an experiment, if you just make hard ellipsoid particles, then experimentally everything just emerges naturally. It's already there. But we want to represent.
We have to understand it.
Yeah.
In the process of it, we have to introduce certain. So there is effective interaction.
Yeah.
So we know it now because we have to. The aligning means they are interacting with it somehow.
Yeah.
So we have to model it somewhere so that we can introduce it in the simulation.
That's
Or
right.
we can do the theory.
Yeah. Yeah.
Ultimate goal is doing theory.
That's right. Yeah.
So because the experiments used to give us the clue
Yeah.
to make theories.
So, one question related to, as you said, that the shape of the particles, that determines whether we can get an orientation or not. So it is an ellipsoid. So
You mean the shape of the particles determine the alignment?
Yes.
Yeah, that's fine. That's correct.
So, mathematically, I was thinking that the shape of the particle, suppose it's ellipsoidal in the beginning, and so ellipse has to a major axis, minor axis.
Yeah.
If we can make it equal, then it will become just a sphere. So
Sure. Yeah, that's fine.
Of course.
Yeah.
So there are models
Yeah.
and you can tune this minor and major axis. Okay, and from ellipse side it can be turned into
That's right.
Yes, spherical shape.
Yeah.
So then instead of then they will start showing some sort of other kind of.
Yeah.
So what will happen that there is an additional degree of freedom now when the particles are ellipse. If they are spheres, they have transversal degree of freedom. Okay.
Yeah.
No reason to talk about the orientational degree of freedom.
Yeah.
But as soon as you make the particle all spherical, there is an additional degree of freedom which enters into the picture. That is the orientation one. So if you just change the density, change the concentration, and lower the temperature, so the easiest thing to manipulate energetically is the orientation basically. So so before it goes into crystalline kind of structure, you will find there are other ordered structures which are due to the orientations.
Yeah, that's right.
This is happening in this particular.
That's right. Yeah.
So I have another question.
Yeah.
That just because of shape we are having these kinds of things, like this alignment or when one link. So
Yeah.
that means realistically, if we see, but like microorganisms do change shapes
You want to talk about flexibility,
Like
elasticity.
if we look at a time scale where the shape is not changing, then it's okay. Say we are looking at a time scale where the shape is not changing, it is just okay. And if it changes shape, his behavior will change. Just say that it has changed from like a
Of course, it will change. Of course.
Yeah,
like
you
if
want
it lose all the alignment, if it just changes from an ellipsoid to speed, just loses all the alignment. If it goes like
yeah, that's correct. Yeah, then to model that, it's gonna be much more tricky. Now, but yeah, that's correct. Yeah.
Sir, and that's about it. In addition to this shape thing, what I wanted to know mathematically is whether if you get from an ellipsoid to a spherical, then does this set of equations resolve to what we did previous?
That's correct. Yeah.
In special cases.
It does. Yeah.
Yes.
Yeah.
That should be.
So if you have a sphere, you don't have this one, okay, and then you can. So we can actually reduce all the equations we have now to the first equation we talked about in the first lecture, right? If you look at these equations here, if we don't have these interactions, we don't have this flow here, okay, right? Then that's gone. This one is gone. What do we have? We just have AVPs diffusing. So we haven't lost anything yet. So we're building up these models systematically in a way that you can always go back and you can always identify. That's also the other point of building models in this fashion.
right because it's linear, right? It's not linear.
Distortions. You look dependence everywhere.
Which one is the?
This equation is linear, right? Linear P, like is this
Yeah.
Can you say add them up?
Also, yeah.
It be a
Very good. So, yeah.
Now you have to be careful now. Okay. Yes. But in this context, it's a nonlinear system, and it's coupled with the flow. What you meant to say is you can add up fluxes.
Scared.
Correct. The fluxes you can, forces you can add up. It's not everything, not always, but yeah. Okay. Other comments? If not, let's take a break.
Yeah.
All right.